Well, let's get started. Introduce our first speaker, Gabriel Shipley, who is a Truman Fellow in National Security Science and Engineering at Sandias National Laboratories, New Mexico, where he chiefly investigates the origins and evolution of 3D instabilities and pulse power-driven implosions. In his research, Gabe simulates small-scale instabilities that form in magnetically accelerating materials on Sandias' Z machine, aiming to understand how those disturbances grow into larger ones. His findings could improve target design models and help physicists grasp instabilities that occur in bigger, higher energy experiments and could inform future accelerator designs. Gabe earned his engineering PhD from the University of New Mexico in 2021. He first began work at Sandias as an undergraduate and continued steadily throughout his graduate career. As a DOE NNSA SSGF recipient, he also completed a 2018 Los Alamos National Laboratory practicum with program alumnus Forrest Doss. Without further ado, Gabriel Shipley.
Thank you. All right. Well, first things first, let's see if the mic works. Okay, it does. I can be heard. Good morning, everybody. It's really a pleasure to be here. I always like to see people from Krell and look back fondly on working with all of them. I see a lot of familiar faces, but a lot of unfamiliar faces in the audience. And to all the incoming fellows, I just want to say welcome. Really glad that you have this opportunity, that you're in the program. It's been a really great time, or it was a great time for me, and the other fellows that have been in the program or have graduated from the program will tell you that for my part, the SSGF was a fantastic thing, and then the LRGF, of course, has been a fantastic thing as well, and the Krell organization is wonderful. So again, really happy to be here and speak to you guys about some of the work that I've been doing, that I've been getting to do at Sandias. I'm going to take a little bit of a broad approach today and dig into a little bit of the details that are pertinent to what I particularly do. But firstly, I'll say, so the talk is going to focus on innovation and advancement of the MagLIF concept on Z. So again, it's going to be a little bit broad, but I'm going to try and focus in on what I've identified as advancements and innovations for this particular program. Advancements meaning incremental improvements of the MagLIF concept, which we'll get into here shortly, and then innovations being sort of off the beaten path, higher risk concepts that I've taken a particular interest in to try and push the program forward in more of a quantum leap kind of way. I'll first acknowledge some of my collaborators here. So Daniel Ruiz, David Yeager, El Arriaga were particularly helpful in preparing this talk. And the rest of the names on this list, which are a small subset of the MagLIF team, of course contributed quite a bit as well. So, okay, let's jump into it. And I'm glad I got some extra time as well. I tend to be overly verbose, so this will help. Okay, so firstly, let's talk about the motivating concept for magnetized liner inertial fusion, and that is inertial confinement fusion. So inertial confinement fusion, ICF, is an exciting field of research and one of very high importance to the DOE NNSA mission space. So going over what ICF is at a very, very high level view, I'm sure most people may be familiar from talks earlier in the week, but I'll just go over here. One of the ways to do inertial confinement fusion, which is laser and direct drive fusion. And so in this approach, what we have here is a little fuel pellet filled with DT fusion fuel. And we use lasers to come in and bombard the inner surface of a gold cylinder or hole rum. So the lasers deposit their energy in that gold wall. The energy is re-radiated as X-rays, and then those X-rays deposit their energy in the outermost layer of that capsule, which explodes outward. And then the rocket force drives the DT gas and implosion in the DT gas, or DT fuel, I should say, to very, very high temperatures, pressures, and densities. And this initiates thermonuclear fusion reactions. Again, very high level view. This is one way to do it. But why are we interested in this? So controlled thermonuclear fusion has applications in nuclear weapons stockpile stewardship, radiation effects science, as well as energy production. So we care about this a lot. We want to learn how it works, how to do it better. And of course, with the great news that just came out of Livermore this past December, we're well on our way to a really, really bright future in this field. At Sandias National Laboratories, we take a slightly different approach. So at Sandias, there's a long history of expertise and leadership in pulse power accelerator science and technology rather than lasers. So Sandias' magnetized liner inertial fusion approach seeks to achieve thermonuclear conditions in pulse power-driven cylindrical implosions. And I show here the MagLIF concept here that we're going to dive into in more detail in the coming slides. So at Sandia, we have the Z accelerator, or the Z machine, which is the largest and the most powerful pulse power accelerator in the world. So going through the anatomy of Z just quickly, this is a 33-meter diameter accelerator. This is a cutaway section that we have here on the upper left. So we charge these capacitor banks at the outer diameter of the machine to store about 22 megajoules of electrical energy. Those Marks banks then discharge on the order of about a microsecond with a 20 terawatt power pulse. And then they start to go through these intermediate storage capacitors and then subsequently into these pulse forming lines to compress that pulse both in space and time. That gives us this blue pulse here, that's 67 terawatts. And then finally in the vacuum section here, we concentrate that energy again in space and time, giving 77 terawatts, and we put that down, put all that energy down, concentrate it down into a little thimble-sized target, a little cylinder about the size of the end of my pinky. And that target is here, it's about a centimeter tall. And so that current, all of that electrical energy gets focused into about 100 nanosecond rise time pulse and down into this small 1 centimeter tall target from starting at this very large power source at the outside of this machine. So compression in time and space, that's the theme of pulse power. So I've mentioned MagLIF a few times. Let's dive into what MagLIF actually is. So MagLIF is magnetized liner inertial fusion. Simply stated, this is the magnetic compression of premagnetized, laser preheated fusion fuel. So here we have a deuterium gas-filled beryllium liner, which is just a fancy word for a cylindrical tube. And there are 3 constituent parts of MagLIF. All of them are very important, and they need to be in the experiment for it to work. And I'm going to dive into the details of each one of these components to explain why they're important and how they work, why we want to make them work better. So firstly, we need to pre-magnetize this target with a 10 to 20 Tesla quasi-static axial magnetic field. This is applied to the fuel by external axial magnetic field coils that I'll show pictures of in the following slides. And we do this primarily, in contrast to laser ICF, we do this primarily to reduce the required implosion velocity compared to laser ICF. So this relaxes that requirement for us and allows us to go into a different regime that is important because the timescales that we have here are longer than what we can achieve in laser ICF. So next, we need to preheat this fuel using an external laser. So the fuel is preheated using particularly the Z beamlet laser, which is right next to the Z facility at Sandia Labs. And we do this in order to reduce the required compressive heating that's required for our target compared to laser ICF. And finally, in the compression stage, the Z machine that I showed on the previous slide, it flows 18 megaamps in about 100 nanoseconds, and that current flows on the outer surface of this cylindrical target. That drives a Lorentz force that pinches the target onto the axis very quickly, and this adiabatically compresses the fuel to thermonuclear conditions. So this is generally how MagLIF works. So each of these components is very complex and has unique challenges tied to it. So starting first with premagnetization, this background axial magnetic field is provided by an external field coil system. That's an external system that has its own complexities, its own challenges. The field strength is actually limited by the coil technology, and there are reasons to think that we want to go beyond the field strength that we're tied to right now. Again, I'll dive into that a little more in a slide or two. As well, the external field coils limit diagnostic access to the target, so we want to be able to see this target as it's imploding with all of our X-ray diagnostics, neutron diagnostics, everything that we can throw at it, and the external field coils limit that in a pretty big way. For laser preheat, the laser energy coupling to the fuel suffers from losses. It's not a perfect deposition of laser energy. So that's something that we'd like to mitigate. As well, the laser energy deposition can exacerbate liner fuel material mix, and this contributes to radiative losses and makes it so that we can't get to the fusion conditions that we want to get to. And finally, in the compression stage, instabilities, implosion instabilities, actually degrade compression of the fuel and confinement of the fuel, which limits our fusion yield. So zooming in on the compression for a second, this is where most of my work is focused on for the last 2 years at Sandia. This is sort of what the compression looks like if you zoom in and take a cross-sectional view from a simulation. You see that this is not a perfect cylindrical compression. What we'd like to have is a nice cylindrical uniform compression being compressed by the magnetic J cross B force, but what we actually have is these instabilities that develop, and that limits our performance in MagLIF. And the last thing I'll say is that each one of these components, again, is complex, but any change that you make to each one of these components feeds into one of the other components. So the system becomes very complex very, very quickly. So let's dive into what MagLIF looks like sort of more in real life and dive into each one of the components in more detail. So on the upper left here, I show somebody holding one of our MagLIF targets, one of our MagLIF liners. So just to give you a sense of scale. And this is it installed, one of those targets installed in the target hardware before we install the rest of the target hardware around it that surrounds it. And then this is what it looks like when it's all built up with this external axial magnetic field coil coming in on top. And basically from this view, we can't see any of the target on the inside. So if we cut away, we can kind of take a cross-sectional view through our configuration to see what this looks like in this cutaway view. So we have our field coils here, our transmission line here that delivers the power, the electrical power to our target, and our target is right around here. So I'm going to dive into each one of the components and try and explain why we do what we do the way that we do. So firstly, for the premagnetization stage, Helmholtz-like coils are used to premagnetize the MagLIF load. So those coils are shown here. There's a coil on the top here and a coil on the bottom, and those surround the target, which again is located right about here. Zoomed in on the target is here on the left. And so why do we premagnetize the fuel? Well, if we look at this schematically in a cartoon sense, charged particles, when they're in a plasma, tend to randomly walk through that plasma. They follow a distribution or a distribution of velocities that they go wherever they want to go sort of in a random sense. However, when you introduce a magnetic field, those charged particles then can get stuck to those magnetic fields. They can precess around the magnetic field lines. For electrons, they tend to precess very tightly around these field lines, depending on the field strength. Ions, it takes a little bit more to magnetize them. But point is, charged particles like to stick to field lines like this and are confined along those field lines if the magnetic field is strong enough. So the field coils that I show here can embed about 7 to 20 Tesla field over a millisecond timescale. The field suppresses radial thermal conduction by suppressing the conduction losses from electrons. So the electrons stick to the magnetic field lines and we don't allow them to lose any energy to the liner as it implodes. And then for the ions, the compressed field, once we compress that magnetic field up during implosion, it actually traps the charged fusion products, which are ions. So we get such strong magnetic fields that we actually get to confine the ions that are produced from the fusion reactions in order to get us more fusion reactions as a function of time during our experiment. So that's why we magnetize. Why do we preheat? So I'll let the video play out here. That's a really, really nice animation. I might actually want to go back and see that again. That's great. To reduce the necessary convergence ratio to reach thermonuclear conditions, the Z-beamlet laser is used to preheat the fuel. So again, this is why we use the laser. Laser comes in from the top here through this broad hole here, and then it hits the laser entrance hole at the top of our target here. So this is the zoomed in version. You can see the laser entrance hole at the top, and the laser comes in and deposits its energy. So the Z-beamlet laser, the facility, there's a photo I show at the middle here, delivers this 2 to 3 kilojoule pulse to the Z chamber directly into our target. So the laser heats the fuel through inverse Bremsstrahlung. It gives us about 100 to 200 EV from a 1 to 2 kilojoule pulse. That's a background temperature that we get from our 1 to 2 kilojoule pulse. And the laser preheat sets the adiabat of the implosion. So it deposits enough energy that we set the fuel on an adiabat high enough so that when we adiabatically compress it, we get to those thermonuclear fusion conditions that we want to get to. Okay, lastly, the implosion phase. So the 20 megaamp peak current from Z is used to compress the liner and the fuel. So you saw a little video of that on the left. This is what it looks like when it's right around peak burn in one of our simulations. And this is a plot that shows as a function of time the liner coming inward. This is radius on the left and time on the radius on the left axis and time on the horizontal axis. And the liner is shown in this gold color, and you can see as that implodes during the current pulse, as you can see in black, the fuel temperature spikes up, and that's where we get our thermonuclear fusion reactions. So the Lorentz force, as I said, accelerates this liner, and the fuel is quasi-adiabatically compressed. And as well, the liner implosion leads to flux compression. So the 10 to 20 Tesla that we have initially gets compressed to order kilotesla, thousands of Tesla, as we reduce the cross-sectional area of this configuration. So we use flux compression to get to those very, very high fields. Okay, so that's why we do each of the three components of MagLIF. This is, again, reminding you what I've already told you a bit, but we have the external B field, the preheat, and the implosion. That's what makes MagLIF, and it results in thermonuclear fusion reactions. So this is a thermonuclear stagnation column. This is an X-ray image that we take from one of our experiments. And so this shows you sort of where the X-rays are being emitted, where the fusion reactions are happening along the height, this 6 to 8 millimeter height of our stagnated fuel column. And this is just to show you some of the characteristic values that are associated, or parameters, I should say, that are associated with an experiment, a MagLIF experiment. So the velocities that we're reaching are around 70 kilometers per second. The radius of the burn column, one of which I show here on the left, or here in the middle, is about 50 microns. The burn temperature, this is an ion temperature averaged over the burn width, is about 2.7 kiloelectron volts. The burn pressure is about 2 gigabar, and the burn width is about 2 nanoseconds. So for those of you familiar with laser ICF, these parameters are going to be quite different from the regimes that they're seeing in laser ICF. Much longer implosions, for one thing. But as well, this is a typical yield that we get, about 2 kilojoule DT equivalent, or at least some of our shots get up to that level. Okay, so that's what MagLIF is. Now let's dive into some of the advancements and innovations in MagLIF that I referred to on my title slide. So I'll start with magnetization yet again. So one of the things that we've been working on over the last few years is trying to advance the level of magnetization that we can put into this system. As it turns out, the magnetization as well as the current coupling, the amount of actual drive current that we can couple to the target, are actually linked through geometry. And I'll show a little bit of that here with these images. So in one instance, we tried to optimize those simultaneously. So on the left here is an image of one of our, say, typical target hardwares or target sets from probably about 4 or 5 years ago. So you can see the external field coils surrounding the target. You can see the target with the deuterium gas colored yellow here, and then a laser coming in green, as well as the power feeds in blue and red here. And so we went from this sort of swooped design here to this conical feed that you can see on the right. This reduced the inductance of our configuration, which allowed us to push more current to our configuration. More current means more force to drive our implosions, which means we can get to even higher temperatures, higher pressures, and initiate more thermonuclear fusion reactions. At the same time, we got rid of the bottom coil and re-optimized this coil design, going to something that is a lot more beefy, more reinforced. We can push more current through this coil configuration using its external capacitor bank system in order to get to higher initial premagnetization fields. And so the plot at the right shows this sort of in plot form, where the red, the dotted line red, corresponds to the magnetization that we were able to get, 10 Tesla, using this configuration on the left. And then the current pulse that you can see in red is what is the current pulse measured at or near the target here for this configuration on the left. So we're hitting about 15, 16 megaamps. Contrast that to what we were able to get to with our configuration in the middle here. We were able to push that current up almost to 20 megaamps, so almost a 5 megaamp increase, which is a lot of force, a lot of pressure that we can now get back into our system, as well as we were able to push the magnetic field up to about the 15 Tesla level. And again, this helps immensely with trying to thermally insulate the fuel and get us to even better thermonuclear fusion reaction conditions. So we're continuing this development, and we'd like to push beyond what we've been able to get to this 15 Tesla level. And calculations indicate to us that greater than 15 Tesla would improve the performance markedly. So we want to get into the 25 to 30 Tesla level, maybe even beyond 30 Tesla. So advanced coil fabrication techniques are being pursued to enable these sort of field levels, 30 and above. And one of the ways that we're trying to get at that is trying to go towards this advanced coil design that you can see an example of on the right, on the bottom here, where we no longer have a rectangular cross-section, but we go to a more advanced setup where we can go into triangular, more sort of triangular cross-section looking things like this, where we go to an orbital winding technique. And we've been able to try and push this towards higher fields. We're trying to push this even further towards this 25 to 30 Tesla level. But there's indications right now with our testing and with the fabrication processes that we've been able to implement that that suggests that this is starting to get towards a sort of ceiling for the external field for MagLIF. We're starting to get to the point where the coil technology is going to become a hard limit. Beyond 30 Tesla is very doubtful. Beyond 25 is really, really hard right now. We're trying to surmount that challenge, but it's tough. So this is starting to become, as I said, sort of a hard barrier for us. And so this is an advancement that we've been trying to take with the program, but is there any sort of innovative approach that we can go to? Any sort of innovation, maybe a wacky idea that somebody has that we can try and implement to try and get away from this? So a path towards magnetization without coils is something that's been introduced, which is sort of an odd thing to contemplate given everything that I've said so far, because the coils are what give us our magnetization. So why would we want to get rid of them? But they're also such a pain because they limit our diagnostic access. They don't get us as high of magnetization as we want. So is there something to this idea? So if the coils represent such a technological barrier, let's get rid of them. Let's see what that would look like. And so this is how we might think to do that. So automagnetizing liners, or automag, offer an alternative path to external coils with several potential advantages. So rather than using an external field coil system, why don't we just incorporate the premagnetization into the liner itself? And how might we do that? We can use something that looks like this, where this is one of our MagLIF targets, MagLIF-like targets, where instead of having a solid beryllium cylindrical tube, we cut away these we put these helical cuts into the cylindrical tube, thereby forcing there to be discrete helical conduction paths in our target. What that means is that when the current from Z flows through this target, we enforce helical current in the target, which enables us to produce an internal axial magnetic field. We encapsulate that with some sort of encapsulant, epoxy encapsulant like EPON, and I'll walk through the steps of how this works, overlaid with a current pulse from Z. So this is a typical current pulse with Z with a little bit of a pre-pulse on the front of it, and we'll walk through what automag looks like. So first we have the magnetization stage. At this point, as I mentioned, helical current flow, helical current flows through the target, and that gives rise to strong internal axial magnetic field, and this gives us fields on the order of 50 to 100 Tesla. We've measured over 150 Tesla on Z, which is actually too high, but point is we can get to very high magnetic fields with this configuration, which is really, really cool. So after this magnetization stage, where we have this slowly rising couple mega amp pulse to put in the BZ that we want, we then go into this stage of the current pulse where we have a more quickly rising pulse, which dielectrically breaks down the insulator that's encapsulating these helical conduction paths. We shift from helical current to axial current, and then as the current ramps up even more, we implode that configuration radially the same way that we would implode a MagLIF liner. So we've been focusing work on this concept using sub-megaamp testing on Mykonos, implosion experiments on Z, as well as 3D modeling in the Sandia code Allegra. So here are some of the results from experiments on Mykonos, which is again a sub-megaamp driver that's at Sandia right next to Z. These are 12-frame images that show optical emission as a function of time during one of our experiments, showing the precession of the breakdown process. Won't go into that in any detail. People can ask if they're interested. So after our Mykonos experiments, we proposed experiments on Z, and were able to actually diagnose radiographically the implosion of automag experiments. So the big question was, how would this helically non-uniform configuration of mass and conductivity, how would that correspond to a cylindrically symmetric enough configuration on Z to be used in MagLIF? Well, we radiographically diagnosed this up to a convergence ratio of 5, and indeed you could see the inner walls here in this radiograph look pretty straight. They look pretty uniform, which is really encouraging for this concept, especially at such a high convergence ratio. And lastly, we've been looking at 3D MHD simulations in Allegra, and I'm about to try and publish these, which is really exciting, but we've been optimizing designs with lessons learned from all the experiments that we've been doing and several iterations of simulations to try and make sure that we understand what we can optimize for in our simulations for upcoming experiments that we want to propose on Z. Okay, let's go to laser preheat. So for laser preheat, the main challenge is trying to couple as much energy as possible from the laser into the D2 fuel without creating mix. So this laser, it doesn't just deposit its energy perfectly into the fuel and keeping everything else equal, it ends up sending out a blast wave into the fuel. It ends up transmitting through this laser entrance hole at the top here, which contributes to losses as well as some mix. And so there are some issues here. So here's a schematic view of the MagLIF configuration showing the laser coming in just in a cartoon sense with the fuel being heated up by that laser. And then here is a hydro simulation by my colleague Matt Wise, showing that it's a little bit more complicated in terms of how that laser comes in, starts to filament in this fuel, spread out, and potentially irradiate the inner surface of the target, potentially contributing to mix of material into liner material into the beryllium liner material into the D2 fuel. So of course the laser preheat occurs by inverse Bremsstrahlung absorption, as I mentioned before. But as I said, the laser must penetrate the LEH foil. So this laser entrance hole foil is plastic, and it has to penetrate through there, and you lose energy to that foil, and then some of that foil gets blasted into your fuel. So how can we reduce these losses, increase the energy deposited in the D2 without making things much, much worse? One of the ways we can do that, and this is the advancement part, this iterative advancement that I've referred to previously, is that we can cryogenically cool this configuration. And what that does is it allows us to go to a much thinner window up here, which is limited by the pressure in our system. So this window is made as thick as it is because we have to make sure it doesn't crack or pop while we pressurize our system. But if we cryogenically cool this, we're able to drop the pressure down by a significant factor, which means that we can thin this window quite a bit, going from 295 Kelvin to 75 Kelvin. We go from about a micron and a half window to a half micron window. That's a lot less foil material for us to try and get through, and a lot fewer losses that we have to deal with. So this is one advancement that we've been working on, and we've been testing it in real time on some experiments on Z. But you might sense a theme here with, if something's a problem, getting rid of it. What if we just think about getting rid of the window? That could be a possibility if we get creative about it, right? So this laser gate concept was actually proposed by Steve Slutz, and it was developed further by Stephanie Miller, an LRGF alumnus, as well as Ben Galloway, an SSGF alumnus, in various ways. And so this is generally what it looks like. We can irradiate the foil with a laser, an external laser, prior to the main laser pulse, weakening that foil in this sort of star pattern here. And then the gas will push away the foil, and then once the foil's out of the way, we can bring in the main current, the main laser pulse, and deposit the energy without having to deal with any transmission through the foil. So it's a really elegant solution, a challenging solution, but a really elegant solution to the problem of having a window here to contain our gas. So these are some tests that we did here where we tried irradiating this foil and breaking it open. And then the LEH foil is something we're trying to optimize as well for this. I won't dwell on that too much more as I'm getting a little bit behind on my time. So lastly, I'll zero in on the compression part of this, which is my own main interest that I've been contributing to with the MagLIF program. So the compression, as I said, is not ideal. We have these things called magneto-Rayleigh-Taylor instabilities that develop. So this is an analogous instability to the RTI, classical RTI instability, where the heavy fluid is the liner material and the light fluid is the drive magnetic field. So this is a fundamental instability that we're having to deal with, and we're trying to mitigate in order to increase the cylindrical symmetry of our implosions. So implosion instabilities, we've found, evolve differently for various target types, and they could be mitigated with dielectric coatings. So first we ran experiments with no magnetic field, and we saw these azimuthally correlated instability structures in our radiographs. So you can see these sort of ring-like structures here. We then magnetized our targets and found that we shifted the MRT to be helically oriented. So you can see these overlaid crosshatch patterns. These are two helices in a radiograph that look like crosshatch patterns because we're seeing through both of them. We then dielectrically coated these configurations, or we dielectrically coated an unmagnetized version. We saw that the dielectric coating leads to much, much less MRTI growth. And then finally, we coated a magnetized version, and what do you know? We see this really nice, stable implosion column here. So this is an advancement that we've made in the implosion side of things. And so the question then becomes, so the coatings seem to work. The coatings reduce the MRT. They make a really nice implosion column. So I guess we're done, right? That's what we do, and no need to study anything more with implosions. That's just what we're going to do. However, dielectric coatings are quite difficult to model in multiphysics design simulation tools, and as well, they mitigate the seed of the implosion instabilities, but not the implosion instabilities themselves. So one of the approaches that I've been working on quite a lot over the last few years is this dynamic screw pinch approach, which essentially you take the standard configuration of MagLIF, shown on the left here in this image, that has axial current flowing in the return current can here and axial current flowing in the target, and you introduce a helically oriented return current can, which introduces a dynamic drive magnetic field component, a BZ component, which we don't usually have in experiments. What this does is it introduces a component that is inversely proportional to the radius of the liner, which is the B phi, as well as a component that is only proportional directly to the current. And thereby what you have is, as the liner implodes, the radius decreases, and so you have this shift in polarization of the overall drive magnetic field, where the fastest MRTI modes as a function of time are stabilized via this dynamic magnetic field line tension. And this is what we call a solid liner dynamic screw pinch. This is actually reducing the implosions in flight, not just the seed. So I've done some calculations on this to try and see what it looks like in terms of simulation space, and for something like a BZ over B phi of 0.5, you can see these simulation cutaway views and opacity maps on the right. We can see a difference between these instability patterns, and we can see a mitigation that we're actually implementing in simulation space, and we want to implement this on Z experiments in order to actually see if the proof is in, or see if we can actually prove this out with experiments. Lastly, I've done some high-resolution simulations of this that indicate, indeed, this is a plot as a function as a function of normalized radial distance moved, the standard deviation of the areal density of these simulations. This is just a metric to show how stable the configuration is. For the Z-pinch configuration in black, you can see these nice azimuthal bands that are very strong and very correlated azimuthally, as I said. And on the same color scale, you can see this screw pinch configuration where things are much, much more stable. And so this is something that we're very excited to pursue forward. There's a 5x difference between a couple of these cases, the BZ over B phi of 0 and the BZ over B phi of 1, and then a 3x difference for the BZ over B phi of a half case here. So won't dive into the details of this because, again, I'm running out of time, and I could talk all day about this. Ask me questions if you'd like. But this is a really exciting pathway to try and stabilize our implosions in a very new and powerful way. So lastly, I'll just leave this up to show you what I've already told you, a little bit about MagLIF, and to aid in any questions. So again, thank you very much, and I'll be happy to take any questions you have.